Okay, so we just looked at the arc definition. Now let's look at the chord definition. This we've looked at before too. If we have an interior angle of D and we have 100 foot of chord, I could bisect this chord so it's 50 feet on the left and 50 feet on the right, and by drawing a line down here, and now the angle here is D over 2, and we already know these are R's, so can I say the sine of D over 2 is equal to 50 over R? Let's look down here. The sine of D over 2 is equal to 50 over R. So R then is equal to 50 over the sine of D over 2. So in both cases, I was able to establish a relationship between the radius and the degree of curvature. So if I'm given the degree of curvature of a horizontal curve, I could find the radius. If I'm given the radius, I could find the degree of curvature. Okay? So because this is based on an arc definition, we have to use, we're using a ratio of the angle to the curve length, and here, since this is based on a chord, which is a straight line, we have to use trig. Okay, now let's define some things in the horizontal curve. Okay, so let's take a look at this, and I'm going to blow it up a little bit. This again is my top view. So my car, I'm seeing the roof of the car, and the roof of the car is driving like this. I see the roof, and it's on a straightaway, and all of a sudden, instead of going straight, it now curves. And this point is called the point of curvature. And you'll notice all the little variables that are used on the drawing are up here. So car drives in on a straightaway, it hits the point of curvature, and now it starts to go on the curve. L represents the length of the curve. Keeps going until it hits here, which is called the point of tangency, and then it starts to go on the straightaway again. So point of curvature is always done on the left. Point of tangency is always drawn on the right when we draw it. But certainly the car going this way is going to hit the point of curvature and then the point of tangency. But when we do the design, we always read from left to right. So left is the point of curvature and right is the point of tangency. Why do they call it point of tangency? This line right here, this straightaway, if it continued, that's called the tangent line. And you notice this is a tangent line as well. And they both, where they intersect is called the point of intersection. The reason that this is a point of tangency is because, if you remember back to geometry, when two things are tangent, there's a 90-degree angle between them. This tangent line, this line that's tangent to the curve, is perpendicular 90 degrees from the radius line that goes to the center of the circle. So this line, which is tangent to the curve, is perpendicular to the radius that goes to the center of the circle. That's why it's called, this is called the tangent line, and this is called the point of tangency. So far we have point of curvature, point of intersection, point of tangency. We have these two T's represent tangent. L represents the length of the curve. C, as you can imagine, represents the chord. R, we know, represents the radius. And delta represents the interior angle that encompasses the whole length of that arc that you're driving on. Let's go back to this degree of curvature again. So imagine you're on a highway and you're driving on a straightaway and all of a sudden it curves. Do you expect the curve in the road to be less than, equal, or greater than 100 feet? You know what 100 feet is now, right? 100 feet is that length of tape. Don't you expect a car, when you're doing a curve on a car, for it to be greater than 100 feet? 100 feet is a short distance, right? So the degree of curvatures are within, let's go back to this picture, are within the delta. The delta is much bigger than the degree of curvature. So there might be 2, 3, 4, 5, 6, 7. There might be 7 degree of curvatures in here. So if the degree of curvature, an example of a degree of curvature is 10 degrees, you might have a delta angle, not of 10 degrees, but maybe of 30 degrees, or 40 degrees, or 50 degrees, or 70 degrees. That would have a number of degree of curvatures in there. So just realize that even though this drawing looks very similar to my degree of curvature drawing, the degree of curvature is just a slice, a smaller slice of what your road is that you're going to be driving on. Okay, the last two variables in here that I haven't mentioned yet is M, which is called the middle ordinate, and E, which is the external distance. So let's take a look at this. M is this line that's coming from the center of the circle that starts at the chord and ends when I get to the curve. So this distance right here is M. And then which distance is E? This distance is E. The distance E goes from the curve to the point of intersection. And I think what I'll do is I'll use some colored markers. So let me pull this down a little bit. So this right here is M. And this right here is E. Okay, and I'm going to draw the rest of the circle here, the rest of the curve. So this is R and R. So looking at this picture, we know now that this is a right angle, right? Because the tangent line is tangent to the circle, is perpendicular to this. And this is perpendicular right here too. If I have a line that bisected my chord, isn't this a right angle too? These are right angles. And I'm going to extend this actually with black rather than using the green. If I wanted to look at the relationship, and what is this here? What is this total angle? Delta, right? So that means this is delta over 2. And this is delta over 2. Bless you.
Thank you.
So if I wanted to establish a relationship between, I'm gonna erase these now, okay? Just now you know where they are. If I wanted to establish a relationship between T and R, wouldn't I use this triangle right here?
Mm-hmm.
Because the tangent of delta over 2, the tangent of delta over 2 is T over R. Does everybody agree? And if I wanted to establish a relationship between C and R, wouldn't I use the smaller triangle? So the first case I used the larger triangle. And now I'm using the smaller triangle because the sine of delta over 2 is equal to C over R. So if I knew delta and R, I could solve for T, right? I could solve for T. If I know delta and R, I could solve for C. But these weird guys in here, these guys right here, I'd like to also be able to solve for. So let's look at E. So I'm going to look at this big triangle that has T here, R here, and delta over 2. And then I have my curve here, right? And this is E. How can I determine what this length is here? Could I use trig and use delta over 2 and R? So let's call this X. All the way from here to here. I'm going to use R, so I'm going to say the cosine of delta over 2 is R over X. So isn't X R over the cosine of delta over 2? And if you remember trig, I don't always remember this, but 1 over cosine is a secant. So that's R secant delta over 2. And if I wanted to find E, if I now know the distance from here to here, don't I know the distance from here to here? Isn't that just R? I just calculated X. X went from the PI all the way down to the origin. And I know the distance from the origin to here because that's my radius. My radius goes from here all the way down here. So E is equal to X minus my radius. Let's try M now. I have a triangle here that has R delta over 2, and now I'm going to call this Y. And here's where my M is. My M is where the curve is. So can I find Y? Isn't the cosine of delta over 2 is equal to Y over R? So Y is equal to R times the cosine of delta over 2. And then wouldn't M just be equal to, what's this whole thing? R minus R times the cosine, well, I'll just say Y. If the distance from here to here is the whole radius, and I just calculated what the distance is from here to here, can I just take this radius and subtract out Y, and now I get my M? It's okay, I can leave it. It's fine.
There's a really bright light from the projector that's in that section.
So the idea is that when you're working with horizontal angles, your radius is given and your delta is given. And then you have to solve for the rest. We were able to solve for T by using trig for the big green triangle. I was able to solve for C using the smaller blue triangle. And then in finding E, I used the larger green triangle again, and then subtracted out the radius. And for M, I used the smaller triangle, blue, and I subtracted that from the radius. Okay. So just keep going over that until you're comfortable. And then in the end, on the bottom of this page, we're actually looking at what all the final equations are for the tangent, for E, for M, and for C. And now, let's go to the bottom. We already knew in the arc definition that D is to 100, the interior angle of D is to 100 feet, as 360 is to 2 pi r. We could also say that delta is to L, because delta represents the interior angle, which is including this length of arc. And remember, we said that D is smaller than delta. So the numerators here all have to do with the interior angle, whether it's delta, the degree of curvature, or 360 degrees. And the denominators have to do with the length of the arc. Here it would be L, here it would be 100, and here would be 2 pi r. And when you convert this, 360 is a regular number, 2 is a regular number, pi is a regular number, 100 is a regular number. I'm establishing now a relationship between, sorry, let me back up. I'm looking at only the relationship between D and L now. Okay, so sorry, we're not using this. This you already knew. I'm looking at only the relationship between D and L. So L would be equal to delta over D times 100. But if you wanted to represent L, that length in stations, then I drop the 100 feet. So if L is 2,000 feet, right, 2,000 feet, that's 20 stations. In the chord definition, we're looking at a relationship here of delta over R is equal to 360 of 2 pi R, right? We could still use this relationship. We could still use this relationship because this is a portion of a circle, here's the delta and here's L, and then the whole circle would be 360 over its circumference of 2 pi R. Okay, let's stop.